Okay, this is the version without without the audio. Okay, can see my screen, class? Huh?
No. Slide, no.
No slide?
Yeah, just, yeah, no slide.
Can see the slideshow?
No.
No. Oh, okay, sorry. Okay. Okay, now can, right?
Can.
Okay, so where we stop? Okay. This is the, okay, there are two. Ada record belum? There are two DC bridges, Wheatstone and Kelvin bridge. Okay. And there are 4 AC bridge. Okay, Wheatstone, the simplest form of bridge for measuring resistance. The most accurate method available for measuring resistance and is popular for laboratory use. It is used to measure an unknown electrical resistance by balancing two legs of a bridge circuit, one leg of which includes the unknown component. Okay, so there is two legs. R1, R2 is one leg, another one consists of R3 and R4. Okay, so one leg includes the unknown component. So let's say this leg consists of unknown component. Let's say R4 is unknown resistor. Okay, so we know the value of R1, R2, and R3. R4 represent the unknown resistor. Fundamental concept is two voltage dividers, both fed by the same input. Okay, so the voltage source will supply the same voltage to the two legs, okay, through this path and through this path. So we can apply voltage divider principle here. The circuit output is taken from both voltage divider outputs. Okay, so this is the circuit output taken from both voltage divider outputs. Okay, we will learn more after this. A galvanometer is connected between the output terminal. So the galvanometer will located here at output terminal. The galvanometer is very sensitive DC current meter. It is used to monitor the current flowing from one voltage divider to the other. Okay, so the voltage divider might be at R2 or R1 or R3 and R4. Okay, but there is a pair of voltage divider here. If the two voltage dividers have exactly the same ratio, then the bridge is said to be balanced and no current flows in either direction through the galvanometer. The bridge is balanced when no current through the galvanometer, no current through the galvanometer here, or the potential difference at point C and D is equal, or the potential difference or the voltage at point C and point D is equal. So the potential across the galvanometer is 0. Vc is equal to Vd. Okay, the circuit will be balanced when Vc is equal to Vd. So VCD or V of the galvanometer is equal to Vc minus Vd. Okay, VCD is equal to Vc minus Vd. VAB is equal to Va minus VAB is equal to Va minus
VB.
VAC is equal to Va minus
VC.
Okay, so Vc minus Vd. So when Vc is equal to Vd, so the voltage will be 0. Okay, so let's analyze the Wheatstone bridge at balance condition. By using voltage divider, we know that VR3 is equal to VDC or is equal to VD, okay, because C is connected to ground, is equal to R3 divided with R3 plus R1 multiplied with VS, because the VS will supply to this. If VS is equal to 10 volts, so 10 volt will flow, 10 volt will be supplied to this leg and to this leg. Okay, so the node voltage at A is equal to VS. VR4, okay, is equal to VBC is equal to R4 divided with R2 plus R4 multiplied with VS again. If we carry out KVL at the lower loop, KVL here, okay, so the notation of voltage drop across the resistors are like this, positive and negative, because current flows like this from A until C. Positive and negative here, positive, negative. So if we apply KVL in this loop, let's say we start with VR3. Let's say we use the first sign, so minus VR3 plus VDB and plus VR4 is equal to 0. For balance condition, we want VDB is equal to 0. Okay, we want VDB is equal to 0 or VD is equal to VB or VR3 is equal to VR4. Okay, so we substitute VDB is equal to 0 and we will get VR3 is equal to VR4. Okay, VR3 is equal to VR4. And we know that VR3 is equal to R3 divided with R1 plus R3 multiplied with VS. VR4 is this based on voltage divider principle. And then we expand the equation, simplify, and we will get R3, R2 is equal to R4, R1. Okay, R3 multiplied with R2 is equal to R4 minus R1 minus times. Okay, so for Wheatstone bridge at balance condition, the product of the resistances of opposite arms are always equal. Okay, the product of the resistances of opposite arm, okay, is are always equal, meaning that R1, R4 is equal to R2, R3. Okay, opposite arm. Note that under resistor can be any of the 4 resistors. Okay, under resistor can be at R4, R2, R1 or R3. But usually, okay, R3 is variable resistor. Okay, the symbol, the arrow symbol here represent the variable resistor, meaning that it is not an unknown resistor. If we carry out KVL at the upper loop, okay, if we carry out KVL at upper loop, let's say we start at VR2 here, and we use the first sign, positive. So positive VR2 minus VDB minus VR1 equal to 0. And we want to make VDB is equal to 0, so VR2 is equal to VR1. VR2 is equal to VR1. And then we substitute VR1 and VR2 like this. This is principle of Akif. This is principle of
voltage divider.
Voltage divider principle. Okay, and then we simplify and we will get R3, R2 is equal to R4, R1. R3, R2 equal to R4, R1. Okay, but please do not memorize the notation of R3, R2 and so on. Please refer to the circuit. Okay, please do not memorize this R3, R2. Sometimes question use notation of RA, RB, RC, or RS, YZ. So do not memorize the notation of 2, 3, 4, 1. Just understand the concept, the circuit. Okay. Or we can write like this. R1 over R2 is equal to R3 over R4. Or R2 over R1 is equal to R4 divided with R3. Or R3 divided with R1 equal to R4 over R2. Or R1 divided with R3 equal to R2 divided with R4. If one of the resistors change even a little bit in value, the bridge will become unbalanced and current will flow through the galvanometer. Okay. So if any resistor change a little bit in value, current can flow through the galvanometer and will not indicate zero. To start the resistor measurement, adjust R2 to make sure that PMMC indicator shows zero. Okay, R2 is variable resistor. We can adjust R2 using bridge null indication principle. For resistor measurement, R4 in circuit is replaced with unknown resistor Rx. R2 is changed with variable resistor. Rg is internal resistance for galvanometer. Okay, so Rg is the internal resistor for galvanometer. If the question ignore the Rg, so Rg is equal to 0. If there is the value of Rg, so you should include Rg in your calculation. Okay. For example, the following unbalanced Wheatstone bridge is constructed. Prove whether the bridge circuit is balanced or not. If it is not balanced, find the new resistor R4 required to balance the bridge circuit. So, if we use a principle of voltage divider, we can write like this. We find VC. VC is equal to VR2. It is equal to 120 divided with 120 plus 80 multiplied with 100. Okay, we get 60 volts. And then we calculate VD, okay, or VR4. It is equal to 160 divided with 160 plus 480 multiplied with 100, and we get 25 volts. Okay, for balance circuit, VC must be equal to VD. Okay, so this is imbalance. 60 not equal to 25. Okay, so not balanced, so the value of R4 is required to balance the bridge. Okay, find the new resistor R4 required to balance the bridge circuit. So we have to find the new R4, or we call it as Rx. Okay, so R4, we know that R1 is equal to R3, R2. Okay, R4, R1 equal to R2, R3. So we want to find R4. So R4 is equal to this. Just substitute R2 is equal to 120 multiplied with 480 divided with 80. And we get the value of R4. So R4 should be 720 so that the bridge will be balanced. Okay?
Doktor,
Yeah.
saya tak faham yang last step.
Yang ni.
Ah,
Okay. Since we found that the circuit is imbalanced, right? Because VC is not equal to VD. Okay? VC is 60, VD is 25. For balanced circuit, VC must be equal to VD, or VR2 must be equal to VR4, or VR1 must be equal to VR3. Okay, so now VC is not equal to VD, meaning that this circuit is imbalanced. So if it is not balanced, find the new R4 required to balance the bridge circuit. So just imagine that we should replace this R4 value with other value. We call it as unknown resistor Rs, or just R4. Okay, what is the new value of R4 so that the bridge will be balanced? Okay, So this is so at balance condition, we know that R1, R4 is equal to R3, R2, right? So R1, R4 is equal to R2, R3. We want to find R4. So R4 is equal to this, and we will get 720 ohms, meaning that when we replace R4 with 720 ohms, then the circuit will be balanced. No current will flow through the galvanometer. Understand?
Faham.
Okay. There is another method. We just use the resistor relationship. Okay. So just multiply at R1 multiply with R4 equal to R2, R3. Okay. So 80 multiply with 160 is equal to 120 multiply with 480. Okay, and we found that the bridge is imbalanced. Okay, because 12.8K is not equal to 57.6K ohm. Since they are not equal, then the bridge is unbalanced, and we use the same expression to find the new R4 so that the circuit is balanced. Okay, so we take out R4. R4 is equal to R3, R2 divided with R1. Okay, and we get the answer. So this approach is easier than the previous, right? Okay. Sensitivity of the Wheatstone bridge. When the bridge is in an unbalanced condition, current flows through the galvanometer, causing a deflection of its pointer. The amount of deflection is a function of the sensitivity of the galvanometer. Sensitivity can be represented as deflection per unit current. A more sensitive galvanometer deflects by a greater amount for the same current. Total deflection may be expressed in linear or angular units such as millimeter, degrees, and radians. Thus, the sensitivity is defined as deflection per unit current, as sensitivity is equal to total deflection divided with unit current. Okay, the formula is equal to D is equal to SI. Okay, D is deflection, S is sensitivity, I is current. What happens if unbalanced condition? Okay. So any questions so far? No question?
No.
Okay. Chapter 5 and 6, DC and AC bridge, contain many derivation. Okay. So you should understand. You should understand the principle of voltage divider rules, Ohm's law, Thevenin. What else? And mathematics. Okay, because there is a lot of derivation in chapter 5 and 6. To determine the amount of deflection that will result for a particular degree of unbalance, the following steps are taken. Okay, so now we learn about unbalanced condition. Okay, unbalanced condition. So meaning that there is current flows through AB, through the terminal AB or through the galvanometer. Okay, at the end of this calculation, we want to calculate what is the value of current that flows through the galvanometer. Okay, because this is unbalanced condition. So there are a few steps. Step 1 to find the equivalent voltage, step 2 to find the equivalent resistance, and the last step is to find the current. Okay, the deflection current, meaning that the deflection current of the galvanometer. Okay. Okay, so bear in your mind that in this subtopic we want to find the current that flows through the galvanometer. Okay, so how to find the current? We know that I is equal to V over R. So we need to find V, voltage. So that's for step 1. Find the equivalent voltage. And then we should find R. I is equal to V over R. We should find R. Okay, find the equivalent resistance. Okay, so for step 1, we call it as Thevenin voltage. Step 2, that resistance is called as Thevenin resistance. Okay, finally, this is the Thevenin equivalent circuit. Current in step 3 is the current that flows through this series circuit, through this equivalent circuit. A and B, meaning that here, current that flows through here, current flows through here. Okay. Equivalent resistance is called as R Thevenin. It is the equivalent resistance of the circuit. Okay. And we have V Thevenin or E Thevenin. It is Thevenin voltage. Thevenin voltage is the VAB. Okay. Is the equivalent voltage here at A, B. Any question so far? Empty, okay?
Ya,
Empty okay tak? Faham?
kita tengok dulu lah macam ni.
Hai, tengok dulu.
Tahu cuaca ni tak ada lah.
Apa dia?
Tak apa.
Okay. So, how to compute the open circuit voltage between terminals VAB? Okay, this is the first step. We want to find V Thevenin. V Thevenin. It is VAB. Okay. Actually, VAB is equal to VA minus VB. Okay. VA minus VB. VA is equal to VR3. Okay. VB is equal to VR4. Okay, but we can put modulus at this equation, okay, so that we ignore the negative value of the final answer. Okay, so by applying voltage divider, since VA is equal to VR3, okay, we know that VR3 is equal to R3 divided with R1 plus R3 multiplied with V. V is the voltage source. Voltage source we supply to this node, okay, and we supply to this leg and this leg. Okay, VR4 is equal to this. This is voltage divider principle. R4 divided with R2 plus R4 and then multiply with V. Finally, V Thevenin or VAB is equal to VR3 minus VR4. So this minus with this. We take out the V here and then we solve for the resistance. Okay. Any question? Ramona, okay?
Okay.
Okay. Okay. Now, how? Let's analyze the VAB on in the upper loop. Okay. So. Okay, V Thevenin is equal to minus VR1 plus VR2. Okay, so V Thevenin, let's say we take the first sign. So minus V Thevenin minus VR1 plus VR2. This is the principle of what? Basam. This is the principle of Basam ada ke tak ni? Kelas, basam ada tak kat sini? Ada. Atira ada? Atira ada ke tak? Atira tak ada eh? Aisyah ada? Mana ni? Tak ada eh? Patut pun tak ada eh? Adalah Atira. Atira? Oh Atira.
Doktor Atira cakap dia punya laptop not responding tapi boleh dengar suara doktor.
Okay, Aisyah ada kat sini? Ada Siti Aisyah? Siti Aisyah? 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 Sami? Sami? Apa pasal semua tak menyahut ni? Kepanggil semua. Alifah?
Ya, doktor.
This is the concept of
KVL.
100. Okay, KVL. Okay, KVL tu je nak tahu.
Doktor,
To make sure that, ya?
kalau macam yang tadi kan, yang lower loop tu, yang tadi,
Okay.
dia tak pakai KVL ke?
KVL? KVL?
KVL.
Actually, we have derived in previous slide, we have derived equation for V-Thevenin or VAB, okay, by referring to the upper and lower loop kan. Ini ya. Belum Okay. Kita tak derive lagi. Okay. So this is lower loop. Okay, lower loop. So we apply KVL in this loop. Okay. Rasa macam kita dah derive tadi, tak derive lagi ya?
Dah derive lah doktor.
Kan tadi kan?
BBB
Kan?
equal to VR3 minus V4. VR4.
Kan? Tapi mana? Ni kan? This one. So we carry out KVL at lower loop. So we get VDB or VAB or V-Thevenin, okay, is equal to VDB plus VR4. Sorry. VR4 minus VR3 minus VR4, okay. And then if we mana apa pula? Apa. Okay, this one is upper loop. Okay, this one is upper loop. So VDB or VAB or V Thevenin here is equal to VR2 minus VR1. Okay, actually this is the same. Okay, so V Thevenin or VAB here, if we apply KVL in upper loop, so V Thevenin is equal to minus VR1 plus VR2 or VR2 minus VR1. Okay, VR1 and VR2. Okay, so we know that VR1 is equal to this, VR2 is equal to this, and V Thevenin or VAB is equal to, we take out V, voltage source, and then we have VR2, okay, VR2, this one, VR2, and then minus VR1. Okay. Okay, so previously we derived for V Thevenin, okay, and then the next step is to find R Thevenin. How to find R Thevenin? I think, have you learned about Thevenin circuit? Last semester tak ada kan Thevenin?
Tak
Tak.
ada, tak ada.
So, how about during diploma? Have you learned Thevenin circuit? Maybe some of you have learned Thevenin circuit. Maybe some of you never learned about Thevenin circuit. Okay, so in Thevenin equivalent circuit, as I said earlier, we have two components, which is R Thevenin and V Thevenin. Okay, so Thevenin circuit means we want to simplify the circuit. Okay, which is finally we will only have one. We will have only equivalent resistance and equivalent voltage. Okay, we name it as R Thevenin and V Thevenin. Okay, so the terminal is remain. Okay, the terminal is A and B here, and then we will have R Thevenin. It is the R equivalent of the circuit, and we will have E Thevenin. It is the voltage of the terminal AB. Okay, so Thevenin circuit deals with simplification. We want to simplify the circuit. Okay. Okay, so we have learned Thevenin voltage. Okay, Thevenin voltage is okay. Thevenin circuit is depends on the circuit itself. Okay, so for this circuit, terminal we should find where is the terminal. So the terminal for this circuit is AB. So V Thevenin is the VAB. Okay, so VAB is equal to VA minus VB. VA here is equal to VR3. VB here is equal to VR4. Okay. If we conduct analysis in the lower loop, but if we conduct analysis in upper loop, VA can be VAB can be associated with VR1 and VR2. Okay, so the next is to find Thevenin resistance. Okay, so how to find the R Thevenin? To find R Thevenin, we set all sources to 0, meaning that voltage source are replaced with short circuit, current source replaced with open circuit. So in this circuit, we have voltage source. So we just short circuit the source. Okay, make it short. If there is current source, we make it open circuit. Okay. And then after we setting all sources to 0, find the resultant resistance between two marked terminals, meaning that between A and B. Okay, this is the original circuit. After we short circuit the voltage source, okay, this path, if we want to redraw the circuit, this path can also be placed at the middle, right? Okay, this path. Make sure the node is remain. And then we have R1 and R2 here, R1 and R3, and then we have R2 and R4. Okay, the terminal A and B can also be redrawn to be placed as this, A and B. Okay, so that we redraw to have a better view. Okay, so that we can analyze better where is connection of series, where is the parallel connection. Okay, so if you can analyze the resultant resistance without redrawing the circuit, so it is good. Okay, so we redraw like this to have better view and to analyze the series and parallel connection. The last step is to find R Thevenin. So when we redraw, we found that R1 and R3 are connected in series or parallel. Sarah? Parallel. Okay, so R2, R4 are connected in parallel as well. Then, so R Thevenin then can be calculated as R1 parallel with R3 and then plus R2 parallel with R4. So we get R Thevenin. Any question?
Doktor, kalau macam yang circuit awal-awal tu, belum potong apa semua R1 dengan R3 tu series kan?
Yes, that's why we apply voltage divider principle earlier, kan? Previously we apply voltage divider principle, kan? Okay, so voltage divider principle can only be applied for series connection. Any question? Faham? Okay, so the next step is to find the current. Okay, so I is equal to V over R, meaning that I is equal to V Thevenin divided with R. If we have R of galvanometer, so we just add with the R Thevenin. Okay, so we have derived for V Thevenin, we have done for R Thevenin, so we can calculate for I that flows through the circuit. Okay, so I is equal to V Thevenin divided with R Thevenin plus RG. If RG is equal to 0, so just V Thevenin divided with R Thevenin. Okay, example. An unbalanced Wheatstone bridge is given. Determine the current through the galvanometer. Okay, if we want to prove this circuit, okay, okay, the question asks to find current through the galvanometer, meaning that this is balanced or unbalanced?
Unbalanced.
Okay, so that's why question asks to find the current through the galvanometer. Okay, so now let's prove that this is unbalanced circuit. Cuba. How to prove?
Divided.
Philip, Emmanuel, Philip, how to prove that this circuit? What is the calculation?
The calculation for the circuit, the unbalanced Wheatstone bridge.
Okay, just let us know how to prove that this circuit is unbalanced.
In order to prove this circuit is unbalanced, the galvanometer has to have some
Proof is your calculation. Proof with calculation. How to prove?
prove with calculation. Oh, okay.
Yes. Cakap je Philip.
Okay, so prove with calculation. A B
Kamarina, how? No need to calculate, just let us know how to prove that this circle is unbalanced. Kamarina? Kamarina, boleh cakap?
Kamarina yang mana doktor?
Kamarina Ahmad Syukri.
Ya. Kalau unbalance R3 dengan R4 tak sama. So kena kira macam mana Sekejap.
Okay, by calculation how to prove? Kamarina Mak Rozi?
Kena kira apa ni dekat A dengan B.
Macam mana nak kira? Apa yang nak kira?
Apa ni? Alah, kejap. Dia
Voltage
kira
divider.
A dengan B.
Okay, voltage divider. Okay, another one method which is simpler. Nurhani, tak pernah panggil nama Nurhani. I think tak pernah panggil kan? Nurhani ada?
Ada doktor.
Okay. How to prove, what is the formula to prove the balance of the circuit? Whether it is balanced or not.
Find the VTH.
Okay, that's the approach to finally find the item I, right? The current of the circuit, the equivalent circuit. Now the first step to determine whether the circuit is balanced or not. Zaim, Akil?
Ya ke?
What's the calculation to determine whether the circuit is balanced or not?
Macam ni.
Faham tak faham soalan saya?
Kena kira dia ni betul. Voltage antara A dengan B.
Okay, that's right. But I want another approach that is that is simpler. Daniel.
Okay, doktor. Ya. So kalau untuk yang second method tu kita kena tengok kat resistor. Kalau kata unbalance R3 dengan R2 tak sama dengan R4 dengan R1.
Pandai. That's right. Okay. So that's the simpler method. So R1, R1, R4 equal to R2, R3 or not? Right. So we found that 1K multiplied with 10K we get 10 mega. Right. 10 mega. Is it equal to 2.5K multiplied with 3.5K? Not right. So it is proven this circuit is unbalanced. Okay, so this is the steps to find the current through the galvanometer because this is unbalanced circuit. Okay, so how to find the current through the galvanometer? We should find V-Thevenin and R-Thevenin. Okay, so how to find the V-Thevenin? V-Thevenin is the VAB here. Okay, VAB is equal to VA minus VB. It is equal to VR3 minus VR4. Okay, VR3 minus VR4 for lower loop. Okay, so this is the formula we take out after we derive for voltage divider principle. Kan? So we take out the V is equal to 6 here. Okay, and then just substitute R3, R1 plus R3 minus R4 divided with R2 plus R4, and we will get the actually you will get minus 0.133 volts. Okay. Actually, for this calculation, we can just ignore the negative value of the final answer because we can put modular sign here. Okay. VR3 minus VR4 meaning that VA minus VB. Current flows from A to B. Okay, but and the notation of VThevenin is positive and negative here. But finally we get minus 0.133. Okay, it indicates that current flows from B to A. Okay, never mind, you can just take the positive value. Okay, this is the analysis for upper loop. Okay, we can write like this, VR2 minus VR1. And we get the same answer. Actually, the final answer for this is minus 0.133 and this is minus 0.133 as well. Okay, settle for VThevenin. This is for RThevenin. Again, this is voltage source, so we short circuit the voltage source. Okay, and then what else? So we found that okay, R1 share the same node with R3 at A and here at B. B, the point of B here is equal to this. Okay, so after we short circuit the voltage source, we can place this part at the middle. Okay, and then we solve for the parallel circuit, and then we add the resultant resistance at the right and left leg, and we get the Thevenin resistance. Okay, and then we can calculate for current that flows through the meter. I is equal to V over R 0.133 divided with R Thevenin that we have calculated previously, and plus with RG, and here RG is equal to 300, just plus with R Thevenin, we get the current 42 microamps. Okay, 42 microamps. Only small value of current flow through the meter. Any question? Any question? Okay, class, remember we have midterm test this Saturday. I stopped the recording here.